Okay, welcome back. So today I would like to say some more things about the Ricci flow on three manifolds. So recall that last time we proved the pinching theorem, the original theorem of Richard Hamilton. So we had given a three manifold compact, smooth, no boundary, and Ricci curvature of B naught positive. Then we had the pinching estimate that the trace-free part of the Ricci tensor satisfies an estimate like this. We had proved this with the maximum principle, and this estimate followed from the fact that Ricci curvature itself is preserved, it's positive, it remains positive. Even more, we had that the Ricci curvature bigger than epsilon times r times the metric was preserved with a fixed epsilon bigger than 0. And this allowed us to prove the pinching estimate, and then we got the convergence of rescaled Ricci flow to space form. So Sn divided by, and in this case it was S3, divided by a finite group of isometries. And the evolution equation that was the key. We had that ddt of the Ricci tensor was equal to the Laplacian of the Ricci tensor minus some tensor Qij, and Qij was quadratic in the Ricci tensor. It was R6 Rik Rkj, the square of the Ricci tensor, minus 3r times Rij, plus a scalar term r squared minus 2 times Ricci squared times Gij. And also this implied an evolution equation for the scalar curvature, Laplace r plus 2 times Ricci squared. And this was the basis for the tensor maximum principle to prove these estimates, and then this. Now, let me add to this, which you can prove by a little exercise. You can also prove, instead of just this lower bound on the Ricci tensor, you can prove a corresponding upper bound. So for 0 less than, say 1/3, less than beta less than 1, can also show that the upper bound, Rij, less than beta times r times Gij is preserved. So you would take the right-hand side minus the left-hand side, call that tensor Mij, and compute the evolution equation, and use the tensor maximum principle like we did last time, and then show you get also this upper bound preserved, just like this lower bound is preserved. Now that is particularly interesting in the case that beta is equal to 1/2. In the case beta equals 1/2, this is just equivalent to saying that the positive sectional curvature is preserved. This says that positive sectional curvature is the preserved properties. Okay. Why is that? Just notice algebraically the if lambda 1, say lambda 2 less than lambda 3 are the Ricci curvatures, are the eigenvalues of Ricci, and such that, for example, lambda 1 is the sectional curvature sigma 1, 2 plus sigma 1, 3, and lambda 2 equals sigma 2, 1 plus sigma 2, 3, and lambda 3 is sigma 1, 3 plus sigma 2, 3. Then you can solve, say, sigma 1, 2. You just solve it in terms of the lambdas, you get 1/2 lambda 2 plus lambda 3 minus lambda 1, sigma 1, 3 equals 1/2 lambda 1 plus lambda 3 minus lambda 2, and so on. Well, there's just one left, sigma 2, 3 equals 1/2 lambda 2 plus lambda 3 minus lambda 1. That doesn't look right. This is lambda 1 plus lambda 2 plus minus lambda 3. Okay? So here you see that, say, for example, this guy here, this can be written as 1/2 the sum of all three of them, which is the scalar curvature, minus 2 lambda 1. And you see that this is positive. This is exactly positive if the Ricci tensor is less than 1/2 times the scalar curvature. So beta equals 1/2 characterizes positive sectional curvature. And let's try to understand the ODE system that we have here by looking at the space of eigenvalues of the Ricci tensor. So consider the ODE system ddt. Let's call this R tilde ij equals minus q tilde ij. Just leave away the Laplacian term for a moment and look at this in how this looks like in lambda space. So you have sort of the three principal curvatures of the Ricci tensor. Here it says lambda 1, and here is lambda 2, and up here there's lambda 3. And since the equation is homogeneous, it is enough in view of scaling to understand the flow, to look at a space where you have sort of one restricted to sort of this, restrict the flow to this triangle, and so restrict to the space where lambda 1 plus lambda 2 plus lambda 3 is R is identical in 1. This is a triangle in the space of positive Ricci curvature. So if you look at this triangle then, let's draw this large. Say this edge here is the one that lies in the space where lambda 1 is equal to 0, so that's at the opposite end. So let's say this one here is where lambda 1 is 0, and this one here is the edge where lambda 2 is 0, and this lies in the plane where lambda 3 is 0. And then in the middle, of course, we have the point where lambda 1 is equal to lambda 2 is equal to lambda 3. And this corresponds geometrically, of course, to the constant curvature metric that you have on S3. Now, inside this whole region here, which is the region of positive Ricci curvature, we are in the positive cone, you have the smaller region where the sectional curvatures are positive, and that is this region here. All right, because say this would be so this would be the sectional curvature opposite lambda 1, so this would be the sectional curvature sigma 2, 3 equals 0, and this here would be the region where the sectional curvature sigma 1, 2 is 0, and finally this one here would be the sectional curvature sigma 1, 3 equals 0. And now what the ODE system is doing, it is preserving this region here. So if we start inside positive sectional curvature, it remains inside sectional curvature. But also if you start inside positive Ricci curvature, you remain inside this region of positive Ricci curvature. And what we've shown with the pinching condition is that the flow is always moving towards this center point. It wants to go to the metric of constant sectional curvature, and even if you come from these directions, you move towards this you come. So that's what our estimates prove, that in this whole region. So now the question is, what happens in a metric of general, without any curvature restrictions? How is the flow behaving if we start somewhere here, or start somewhere here where we don't have positive Ricci curvature? What is the flow doing in those cases? Now it turns out the really critical points are these ones here, because here and on these points here we have something where two of the sectional curvatures are 0 and only one is non-zero. So for example here sigma 2, 3 would be 0 and sigma 1, 3 is 0, and the only one that is not 0 is sigma 1, 2. So this would be the case, for example, geometrically, where, so here is sigma 1, 3 equals sigma 2, 3 equals 0, and this would correspond to S2 cross S1 or S2 cross R. So at this point we have the geometry of a cylinder where you have just one sectional curvature for the cross-section of the cylinder, non-zero, and the two other sectional curvatures where one of the directions goes in the flat direction are both 0. So these critical points, they actually occur as geometric situations which are right on the boundary of both positive Ricci curvature and positive sectional curvature. So it turns out these are particularly critical points, and now some beautiful theorem that Hamilton and Ivy proved is that even if you start outside, then slowly the flow will either take you inside, or at least it takes you to these points here. So you get to the region of positive Ricci curvature, but you may not end up really inside. You may sort of flow slowly into one of these critical points. So the estimate that proves that is rather delicate, and that's something I would like to show you, because we can do it with the evolution equation for the Ricci curvature and for the scalar curvature that are here on the board. Now, to explain the estimate, we need to look at a special function, because the estimate is rather delicate, involves a logarithm. And so consider the function f of x equals x log x minus x. Then you get that f dash of x is equal to 1 on x times, you get just log x, and therefore f double dash of x equals 1 over x. So it's a convex function, and it looks like this. Here you have y, and here you have x, and here you have 1, where the function has a minimum, and the minimum is minus 1. So it comes through here, and then it goes through E, and then it grows a little bit faster than mod x. And now from here on, so on the set where x is bigger than 1 and infinity, it's, f is increasing and convex. So it has a reciprocal, so that f inverse be the inverse function. So f inverse of y is x, and this is y. And then you get here, if you take the diagonal, which crosses at e squared, if you take the diagonal, then this goes from, here's minus 1, and here is 1, and here is e, then, yeah, I'm not good at drawing this. you get here the function f inverse, which is always above 1. And f inverse, of course, then grows slower than linear. So notice that the limit of y tending to infinity of f inverse of y divided by y is equal to 0. Okay? So we have sort of this delicate logarithmic deviation from linear growth. And that function is useful to measure such a delicate estimate as we need. The other piece of notation that we need is write Mij to be the tensor which we want to be positive in the case of positive sectional curvature. So we take R times Gij minus 2 times Ricci. And then, as we have just seen from this little algebraic computation that I showed you, the eigenvalues of this tensor are just twice the sectional curvatures. So the eigenvalues of Mij are twice the sectional curvatures. Let's call them, say, kappa 1, kappa 2, and we order them. The smallest one is kappa 1, and we order them from kappa 1 up to kappa 3. And then the theorem, which goes back, which was first proved by Richard Hamilton and Tom and Ivy, says that if you start with a manifold, a three-manifold compact, if M3 G0 is a Riemannian three-manifold, as before, compact, no boundary, smooth, with scalar curvature bigger than -1. This is just a normalization. And with this tensor Mij plus f inverse of the scalar curvature. It's now defined because the scalar curvature is bigger than -1, so it's defined. If this thing here times Gij, if this matrix is positive at t equals 0, then this remains so under, then this inequality remains true for t greater or equal to 0. In other words, this inequality is preserved under the flow. Now, we know that Mij greater or equal to 0 is preserved. That's just the fact that Ricci curvature less than 1/2 a scalar curvature is preserved, which is equivalent to saying positive sectional curvature. Now here, this says that Mij is bigger than minus this thing. F inverse is a positive term. So Mij is bounded from below by something negative. So even if you don't make any assumption on the manifold, rather than fixing some scaling, then we get some estimate from below. And this estimate is such that, because of this property here, it's such that, remember this scales like scalar curvature, So if you divide by scalar curvature, it means the eigenvalues up to rescaling, the negative part of it tends to 0. So the negative part, this estimate says that the negative part of the sectional curvatures after rescaling tends to 0. In particular, where the curvature goes to infinity, where we have blow-up, at those points, the sectional curvature after rescaling has to be non-negative. Let's formulate that as a corollary. Corollary. So first of all, it's the sectional curvatures just kappa I is 1, 2, 3 of M3 G of t solving Ricci flow satisfy that the negative part, so the minimum of sigma divided by r and 0, minimum of kappa I for our sectional curvatures divided by r, so it's a scaling varying part. This is little o of r, little o of 1 as r tends to infinity. And as a corollary, we get that and this, since we haven't done rescaling of general singularities yet, but as a corollary, it's clear that any smooth rescaling of a singularity, or if t tends to a maximal time interval, finite time, so suppose we have a singularity at some finite time and we approach the singularity, then by rescaling, the negative part will go away as r tends to infinity, and therefore we have that any smooth rescaling of Ricci flow in 3 dimensions has non-negative sectional curvature. Which is a key step in understanding the possible singularities in the general case. So on the way to the Poincaré conjecture, this and the geometrization conjecture, this result of Hamilton in Ivy was one very important step. Now, how to is there anything else I wanted to say? Yes, this, by the way, is not true. So remark. This is not true in higher dimensions. A similar result is not true in higher dimensions. So in higher dimensions, you can have more complicated singularities where you don't have this nice feature. So now, for the proof, first, oh right, there's one more remark I want to make before I do the proof. It seems like in the theorem, like this assumption here and this assumption there are some restrictions on the initial metric. They are not, because you can always rescale your initial metric to achieve both this inequality and that inequality. So, given an arbitrary metric G0 on M3, we can always find lambda bigger than 0 sufficiently large such that lambda G0 satisfies that the scalar curvature is greater than -1 and even each sectional curvatures are bigger than -1 for all I equals 1 up to 3. You just have to dilate because there will be some negative lower bound on the sectional curvature and then scalar curvature on your initial metric, and if you do scale, just blow it up sufficiently, then you can achieve these inequalities, and then because f to the -1 is bigger than 1, make sure that this inequality is true initially. You could have also have formulated this with a slightly changed, rescaled function f to deal with any metric, but this is a cleaner presentation. Okay, so this is not a restriction, this is just a normalization. Now, to prove the result, of course, you want to use the tensor maximum principle, and we also already proved the tensor maximum principle, and I don't want to deal with all the Laplacian and gradient terms again because of this logarithm. It will just be a little bit messy, but since f is convex and f inverse is concave, it is true proof, note that the region of kappa 1, kappa 2, kappa 3 such that our two inequalities kappa 1 plus kappa 2 plus kappa 3, well, this is just R, is greater than -1, and the requirement that the first one, the smallest one, kappa 1 plus f inverse of kappa 1 plus kappa 2 plus kappa 3 is greater or equal to 0. This region here, these are the two conditions that we want to be preserved. This region is convex and closed. Is closed and convex. And then our tensor maximum principle, in particular in the general form that I stated in the remark in the last lecture, says we only have to check that the ODE system preserves this closed and convex set, and then the PDE will also preserve it. You just have to look at the boundary where this inequality is threatened to be violated, that at the boundary the solution is pushed in by the ODE. So only need to show that the ODE system for kappa 1, kappa 2, kappa 3 preserves this region, and that means I have to show that at the boundary point, in other words, where you have equality, one of these inequalities, the ODE doesn't take you up. The ODE pushes or points inwards. Okay, this was our null eigenvector condition in these simple cases. Okay, so what is the ODE system for kappa 2, 1, kappa 2, kappa 3? Well, from ddt of Rij equals minus Qij, this ODE system that we had, where the Qij was this tensor that started with Rik, Rkj, and so on. A little computation shows that you get the following very nice system. You get ddt of kappa 1 is kappa 1 squared plus kappa 2 kappa 3. You get ddt of kappa 2 is equal to kappa 2 squared plus kappa 1 kappa 3, and you get ddt of kappa 3 is kappa 3 squared plus kappa 1 kappa 2. That's the system we're dealing with. Nice ODE system, and we know already that the first inequality is preserved. Remember, we had proved this by looking at ddt r equals Laplace r plus 2 Ricci squared, and then since this Ricci squared term is positive, any lower bound on the scalar curvature is preserved. But of course, you can also do it in this kappa space and use these equations here. At the ODE level, we would just have ddt of kappa 1 plus kappa 2 plus kappa 3. Well, it has to come out exactly 2 times Ricci squared, and when you do it, yes, indeed, you get kappa 1 squared plus kappa 2 squared plus kappa 3 squared plus the cross terms plus kappa 2 kappa 3, which you can regroup to see that this is kappa 1 plus kappa 2 squared plus kappa 1 plus kappa 3 squared plus kappa 2 plus kappa 3 squared, and take the whole thing times 1/2, which is, of course, the same as this. Okay, so the first inequality is certainly preserved, so we have just to concentrate on the second inequality. Now, to prove the second inequality, rewrite this. So the second inequality was that kappa 1 is bigger than minus f inverse of kappa 1, kappa 2 plus kappa 3. And the yeah, you can also this is not so clever, right? Like this. This is bigger than minus kappa 1, it's the same thing. And apply f to both sides. So this is the same as saying that kappa 1 plus kappa 2 plus kappa 3 is greater or equal to f to the minus f of minus kappa 1. Right. And now the function f, remember, was x log x minus x. So this is minus kappa 1 times log of minus kappa 1. X log x minus x, so plus kappa 1. So this, remember, we are dealing now with the point, at the point where the smallest sectional curvature, which is kappa 1, is negative. So this makes sense, right? So we have here in this setting, it's rather it's nicer to deal with a positive term. So set n equals minus kappa 1, okay? So which is now greater or equal to 0 if we are at a point where we have equality. We just have to look at boundary points, and at the boundary points where we have equality, minus kappa 1 must be positive. And then we get that we want to show that kappa 2 plus kappa 3, because the kappa 1 cancels, that kappa 2 plus kappa 3 is greater or equal than n times log n. Now, if we have equality, in other words, on the boundary of the region, that's where we have to check that the ODE points inward. If we have equality, we can solve for log n. We can solve that log n is equal to kappa 2 plus kappa 3 divided by n. Okay? And so now we have to compute what is ddt of this thing. We have to show that this is preserved. So we compute ddt of both sides. So using our from the ODE system for the kappa i's, we get that ddt of kappa 2 plus kappa 3. So this is kappa 2, yeah, that's right, this is ddt of kappa 2 plus ddt of kappa 3. This is kappa 2 squared plus kappa 2 kappa 3 plus kappa 3 squared plus kappa, no, kappa 2 squared plus kappa 1 kappa 3 plus kappa 3 squared plus kappa 1 kappa 2. And this is supposed to be, we have to check that this is true, that this is bigger than the derivative of the right-hand side. So this is the derivative of minus kappa 1. So this is, if I differentiate this, I get the ddt of n times 1, but if I differentiate the logarithm, plus log n. And ddt of n is minus ddt of kappa 1, so this is minus kappa 1 squared minus kappa 2 kappa 3 times 1 plus log n. And log n, I substitute kappa 2 kappa 3 divided by n. Okay? Now, this here, together with that there, combines, multiplying by n, this combines to the requirement that if you regroup, you get kappa 2 squared plus kappa 3 squared here times n, and then you have plus kappa 2 kappa 3 times kappa 2 plus kappa 3 plus n plus n cubed is greater or equal to 0. And here I should say I do the computation like this, and I do this regrouping in case kappa 2, kappa 3. So if we have equality here, so this is non-negative, right? So here, since kappa 3 is bigger than kappa 2, this means certainly kappa 3 is greater or equal to 0. But kappa 2 I don't know yet. So now if we, in the case first, that the kappa 2 is greater or equal to 0. If we are in that setting, then we are done, because then all these terms here are greater or equal to 0. So then, done. Now, in case that kappa 2 is less or equal to 0, which could also happen, regroup differently. Okay, regroup with m equals minus kappa 2, and then you can regroup this computation here and see that you end up with lambdas with kappa 2 squared minus kappa 2 m plus kappa m squared times n minus m, which is n minus m plus m cubed plus n cubed greater or equal to 0. And this thing here is also true because n, kappa 1 was the most negative one, so n, the minus kappa 1, is bigger than minus kappa 2, so this is non-negative, and here we can complete the square and see, because there's no 2 here even, this is also greater or equal to 0. and this is greater or equal to 0, and these two are greater or equal to 0 anyway, so they are also true. Also okay. So this proves the whole thing. So the inequality is preserved, and therefore we have this lower bound on the sectional curvatures. We had already seen very early on that there was such an improving lower bound for the scalar curvature, but this is much more delicate because it says if the scalar curvature blows up, and that turns out the only possibility that a singularity can occur in this three-dimensional case, then all the sectional curvatures have to be compared to the scalar curvature almost positive. With a very delicate logarithmic estimate, but that turns out to be enough to show that all these scalings have no negative sectional curvature. And that means that the singularities are much more restricted than you would expect from the original solution. There was no initial curvature assumption on the original solution or on the initial data, and still the flow prefers non-negative curvature. Now, to compare this with mean curvature flow, comment there. The situation there is different because in mean curvature flow, as I pointed out before, there is no such preference for a certain sign of the mean curvature. If you look at the evolution equation for mean curvature flow, so comparison to mean curvature flow, remember there we had ddt of the second fundamental form, or Laplacian's second fundamental form, plus a squared, the second fundamental form, if we have ddt of f equals mean curvature vector in Euclidean space. And in particular, we had ddt of the mean curvature was the Laplacian of the mean curvature plus mean curvature times a squared. Now this term here is completely symmetric between positive mean curvature and negative mean curvature, very different from Ricci flow. However, it turns out if you know that mean curvature is positive, say positive on Mn0, then this is preserved. And it turns out you can then prove a similar theorem to the Hamilton-Ivy theorem in all dimensions. And this is a theorem of myself and Carlo Sinistrari. Sometimes some time ago, it appeared in Acta Mathematica. And it says that if the mean curvature is positive on the Mn0, then the principal curvatures lambda I of the second fundamental form satisfy exactly the same thing, that the minimum of lambda I divided by h and 0 is little o of 1 if h tends to infinity. So the non-convex part of the second fundamental form goes away, and you get that all the scalings of singularities, in this case of positive mean curvature, yield weakly convex rescalis. Again, solutions of mean curvature flow. So just like in the three-dimensional Ricci flow, the Hamilton-Ivy estimate says that for any initial matrix, you get non-negative sectional curvature after rescaling. In mean curvature flow, you get in this restricted case of positive mean curvature, otherwise you cannot expect it. You get that all singularities are weakly convex. But as in other comments I made, here this is not possible to prove this with the maximum principle. It has to be proven with the help of the diffusion term. So here the proof requires the use of the diffusion part of the equation, and you need Sobolev inequalities and Poincaré type inequalities. It's all integral estimates to prove this theorem. Very different from Ricci flow, but the spirit of the result is exactly like the result of the Hamilton-Ivy estimate. And that's the lecture on this topic. Thank you.